So in general, practical on-chip inductance on the neighborhood of 10 nanohenry on down. A slightly more complicated formula they have designed, it is going to yield a better accuracy. So the 37.5 mu naught n square a square by 22r minus 14a. So here we consider the area and the radius, and we have this formula which is going to be a better approximation for the inductors. And this formula has an error of less than 5%. But the previous formula, whatever we've seen, it has a tolerance of more than 30%. So the error will be 30%, which is very, very high. But this formula is going to have an error of under 5%, which is going to be considered very good. And also, this formula accommodates for hollow inductors. So hollow means inside the inductor, inside the wire, you will have a hollow space. Either you can fill that hollow space or you can have it as it is, that is left to the designer. Okay, so if you fill that hollow space, you will have additionally mu naught into mu r coming into the picture, so L value will increase. So additionally, having that space filled with the material will increase the inductance of your spiral inductor. And aside from the large areas, potentially another serious problem is that they are going to have a serious larger losses. So more number of turns you are going to have, the inductor is going to have more number of resistance. So more resistance, more thermal noise, more power loss. So everything is going to make it not suitable effectively for RF applications. And you have the resistive losses, the skin effect will be there, and at RF frequency range, the current distribution becomes non-uniform. So which will start producing radiation effect. So instead of the current traveling to the inductor, the current starts radiating from the inductor. So which is going to be a serious issue at RF. So when you reduce the area, the resistance will increase. R is equal to rho L by A. So when you reduce the effective area of inductor, the resistance value is increasing. So if resistance value is increasing, thermal noise will increase, the power loss will increase. So all other things are going to think. But we have seen that if the inductance value has to be large, N value has to be more. Okay, so everything is related. So we have to compromise on either the area or the inductance or the resistance. So accordingly, we have to choose proper trade-off between the parameters for using them in RF circuit. So L and C will oscillate. So wherever you have L in your chip, nearby that L, you will have a series or parallel C, so that they resonate and produce a resonance effect. The resonant frequency, it is going to be 1 by 2 pi root of LC. So you know that formula. And when you're going to have this resonance effect, you have this additional shunt capacitance coming from the inductance. So inductance produces a shunt capacitance which is going to overlap with the capacitance already present in the resonance circuit. So this they found that this shunt capacitance is going to have a very negligible effect. So otherwise, the series of these capacitance will appear across the inductor. So even though you have a parasitic effect in your inductor, but that is very, very negligible. So it is not going to pose a serious issue in fabrication. So this is going to be the final fabrication of your resonance circuit. So an effective ground shield may be even considered of polysilicon. So this is going to be the substrate or effective ground. So it is allows one to save precious metal layers for inductor oneself. So you see practical inductor series with resistance you will have. Parallel to capacitance you will have. So these are the oxide layer capacitance, and these are the capacitance which is available at the source side and at the drain side. So here we have a resonance circuit L parallel to C. Okay, so and this L is going to be the spiral inductor. And we are going to fabricate CP very close to L so that both of them resonate and produce the necessary resonance